Hi, my name is Mike from Effortless Coding, and in this video I'm going to talk about constructing binary search trees. So if you're a software engineer who's trying to keep his interviewing skills sharp, perhaps you're thinking about switching to a better job, or you're somebody who's trying to get his first job and wants to clear those interview rounds with flying colors, this video series is for you. I'm going to cover all the popular data structures and algorithms companies out there like to ask you. So in this particular video, let's dive into binary search trees. I have to warn you, this is a pretty in-depth video and you might want to dedicate about 30 minutes of your time just to have full focus on what's going on here. And if you want more explanations like this, click the like button below and that will tell me that this video series is worth making. So before we go into constructing a binary search tree, let's first understand what a binary search tree is. So for that, you need to first know a few concepts. So you obviously need to know what a binary tree is in the first place. And a binary tree, simply put, is a tree data structure in which each node has at most two children, which are referred to as the left child and the right child. Sometimes they're called the left child, the left leaf and the right leaf. A binary search tree is a subset of binary trees where each node can have subtrees, commonly noted as left and right, and the most important part here is each node satisfies what's called a binary search property. A binary search property states that the value in each node must be greater than any value stored in the left subtree and less than or equal to any value stored in the right subtree. Now I have to warn you that in some places the definition could be slightly different and these conditionals could be swapped around. So in some places they might say that the value in each node must be less than any value stored in the left subtree and greater than or equal to any value stored in the right subtree. Similarly, they could swap the strictness of the comparisons. But no matter how these comparisons are placed, the general approach to constructing a binary search tree doesn't really change that much. And you can easily change up your approach depending on which definition you get. So let's actually look at the visual representation of a binary search tree because that can help you understand this concept a little bit better. So here's an example of a binary search tree, and as the definition stated, it's a binary tree. So we have nodes, they have leaves or children, and each node satisfies the binary search property. So let's look at the node 13. It is strictly greater than 10. It is less than 15. So similarly, 13 is actually greater than 12, 9, and 10. So it's greater than anything on the left side of it. And it's strictly less than both of the 15s. So that's how you can tell that it satisfies the binary search property. And here's an example of a binary tree that is not a binary search tree. The only difference here is I swapped the value 10 with value 13, and suddenly these three nodes no longer satisfy the binary search property. This node 13 is not strictly less than this node 13, so its value is no longer strictly less than any value in the left subtree if we go back to the definition. So that's why this entire binary tree is no longer a binary search tree. All right, now that you have a good idea of what a binary search tree is and what it looks like, let's look at the three most common operations that are used on the binary search trees. The first one is inserting a new element into the tree. Second one is finding a node or finding if a value exists in the tree. And the third one is removing an element from the tree. So let's start with operation number one, inserting a value into a binary search tree. How would you do that? The way to insert a value into a binary search tree is quite simply accomplished by using the binary search tree property. And the way you do it is you first take the root node, you go node by node, but instead of checking every node in a tree, on each traversal you check if the value you're trying to insert is greater than or equal to the current node's value or less than the current node's value. If it's greater than or equal to the current node's value, you traverse to the right side. And similarly, if it's less than the current node's value, you traverse to the left side. And you do that until there's no leaf to traverse to. And if that's the case, that's where you insert the value that you're trying to insert. If we were trying to simulate this, it would look something like this. Let's say I want to insert value 9 into this binary search tree. So again, I start with a root node. I check if 9 is greater than or equal to 5. And of course it is. So I traverse to the right subtree. Then I check 9 with 13 and it's less than 13. So I traverse to the left subtree. Similarly, 9 is less than 10. So I go to the left side. Here we can see that 9 is equal to the current node I'm traversing through 9. So based on the property of the binary search trees, I need to go to the right. And similarly, here's the last node in the tree because it has no leaves and I'm trying to traverse to the right and there is no right leaf. So the conclusion here is to insert 9 to this spot. And this is how you insert an element into a binary search tree. The source code would be something like this. It will be provided below the video, so you can check it out and run it locally. But the way it works is you first set the node to the root node, then you start a loop where you check if the value is less than the current node's value. If it is, then you traverse to the left unless the left node doesn't exist. If that's the case, then you basically create a leaf node and you determine that the value has been inserted into the tree. Similarly, if the value is greater than or equal to the last node's value, the current node's value, then you do the opposite. You either traverse to the right if the right node exists, or you insert the node to the right and exit the loop. Okay, now let's move on and go over the operation that checks if a value exists in the binary search tree. It's pretty much the same operation as looking for a specific node by its value. The way to do that is actually very similar to insertion. And again, we will be using the binary search tree property to accomplish this. So let's say we're trying to check if a certain value exists in this binary search tree. You would go node by node, but you start with the root and you don't check every single node in the tree, of course. But instead you use the property and you check if the value is greater than or equal to the current node. If that's the case, then actually, let me correct myself. You don't really check if the value is greater or equal to the node. You check if it's strictly greater than the current node. Then you traverse to the right side. If it's strictly less than the current node's value, then you could traverse to the left side. Because if it's strictly equal to the current node's value, then it simply means that we have found the node and you can return either true or the node itself, depending on if you're trying to check if the value exists or you're actually trying to retrieve the actual node. Now, if you traverse all the way to the end and you have not found the value, then you just return false or null. again, that just means that the value doesn't exist in the tree. So let's do a simple simulation and check if the value 12 exists in this binary search tree. So I would take the 12 and compare it with the root node's value, 5, and I can immediately see that 12 is greater than 5. Then I would go to the right side, check 12 with 13. It's less than 13, so by the search property, I need to go to the left subtree. And similarly here, I would check 12 with 10. It's greater than 10. I would go to the right subtree. And here's where I found a node that's strictly equal to the value I'm trying to check. So 12 is equal to 12. So with our node, that's the answer. The code would look something like this. Now, I've modified it a little bit, and I'm returning here both the node that contains the value and the parent right before the node. The reason I do this is because it's going to be useful during the operation number 3, removing the element. So let's go through this code. You can, again, find it below the video. I'll host it on GitHub. In order to find the node by value, or to check if the node exists, you first check if the value is equal to the root's value. If that's the case, then you pretty much found the node itself, and obviously the value in this case exists in the tree. Then you start a loop, and you hold the reference to the parent of the current node and the next node, or the current node you're iterating through. And again, you do the comparison that was mentioned in the previous slide. You check if the value is strictly equal to the current node or the next node's value. Obviously in this case, that's the case. So if that's the case, this line of code literally returns that node. If not, then you need to check if you need to go to the right side or the left side. So you check the value with the current node's value, and then you determine if you need to go to the left or the right side. You stop the loop when either left side doesn't exist or the right side doesn't exist. And that's basically how the algorithm works. All right, on to the next and the last operation that you need to know about when it comes to binary search trees. It's removing an element, and by far it is the most complicated operation out of all to implement, and you'll see why in a moment. So removal process has some difficulties. It's not as straightforward as the 2 previous operations. So the way you go about it is you need to first find the node that you want to remove using a similar algorithm you use during the implementation of the contains operation, and then you need to properly remove that node. So the reason why this operation is difficult to implement compared to the other 2 is because when you remove a node, let's say I remove 15, I need to put something in its place. And it's sometimes easy to figure that out. Let's say I remove 12. It's easy to move 10 upwards and it would still work. However, it's not always as easy. If the node has 2 leaves, 2 children, let's say I'm removing 13, it's no longer that simple to just move one of the subtrees upwards, because if I try to move 15 upwards, suddenly I have this tree with 3 children. It doesn't make sense. It's not a binary search tree for sure. So instead of moving an entire subtree upwards, you need to also account for the cases when it's not so simple. So the way you do it is, instead of rearranging the entire tree, which is a very naive method and very costly in terms of time operations, you need to replace the value of this node. Actually, let's go to the next slide. Yeah, so when you remove a node from tree, you can take a value from the right subtree and replace it with the value from the node you're removing, as long as it satisfies the BST property. So in this case, if I remove the 5, what I would need to do is I would need to find, let's say, 6. I would need to find 9. So I would put 9 in this place. Then I would take the parent of the 9 and I would just, remove 9. As you can see, it keeps the BST property, and we effectively removed an element from the tree because 9 is still greater than the left subtree 3. The values in the left subtree, which consists of only just one value 3, and 9 is strictly less than any value on the right subtree, so it's less than 15, those 10s, and 16. Alright, so this is the code for removing an element. It's in JavaScript. You can get that code below the video. There will be a link to it. But I'll do something different, right? Because for this particular scenario, I think you need a visual representation of what's going on. So instead of just showing you the code and letting you figure out on your own what it does, I figured that giving a visual representation will be much better at explaining what the algorithm actually does. And specifically for this, I also came up with this scenario with a lot of values. As you can see, I'm running out of integers, so I had to use decimals. And let's say our goal is to remove 13 out of this binary search tree. Cool. So the way we do it is we reused findNodeBST from the previous part of the video and if you don't remember it, just rewind back to operation number 2. It basically finds the node by its value. So we're trying to find 13. It will find us this node. Let's illustrate it by putting pointers over here. This is what the function findNodeBST would find us. Then if it didn't find the node, then it doesn't do anything. That means we're trying to remove a value that doesn't exist in our binary search tree, which is not the case in this scenario. So in our scenario, this line would start executing. And this algorithm specifically tries to traverse the right side, because if you do the same thing on the left side, you can end up with you will end up with 10 over here, and 10 actually doesn't really satisfy BST because it's not strictly greater than this 10. You can try it on your own by just replacing node right with node left and trying to do something similar but kind of in the opposite direction. I'll explain to you the variation that works. Okay, so we need to traverse the right side, not the left side. So what I need to do here is I would first instantiate some pointers which we will use during our while loop. So IT node will be specifically the very next node from 13 that we just found, and then we'll kick off the loop. What we're trying to do here again is we're trying to replace 13 with some value that is less than or equal to 14. So what if we know where 14 is and we know BST property, all values on this left subtree from 14 will be less than or equal to 14. So we need to take the values from the left subtree, right? Now the only thing is the value that we take from here must also be less than or equal to any value that we kind of have left over. You'll see in a second. So that's what the algorithm tries to do. Let's get to the end and you'll see that basically what's going to happen. So we're going to traverse to the left side because we know that on the left subtree we will find a value that satisfies BST property. So we keep going until there is nowhere left to go. It would be somewhere in this state. This is the... So, yep, you can try execute it on your own, but this is basically the end state after which the while loop will exit. Because at this point, 13.3 does not have a left child. So what we do is we replace our question mark with the IT node value. So we put in 13.3 here, and if this if else condition basically checks if IT node was the left or the right child of prev node, and obviously because we've always been traversing to the left side, this IT node will always be the left child of previous node, unless we couldn't traverse it at all and the previous node was, at the very beginning, and IT node was here. It's like, let's say this entire subtree did not exist. Yeah, and then that's why the this condition checks for the other possibility where IT node is actually to the right side from previous node. But in our example, it's always going to be on the left side. Cool. Hopefully that's clear. And what we do here is, okay, we have replaced the value 13.3, and pay attention that 13.3 satisfies the BST up to at least this point, like this point. So it's less than 14, 16, it's less than 15, it's less than 13.5, it's less than 13.4. Now we need to remove this value that we just used to put here, and okay, so the previous node left was equals to IT node, so this is our condition. We need to replace the left connection with the IT node's right connection. So we basically point this to this, and let's check it again if 13.3 satisfies our BST property, and it does. So 13.3 less than everything here, and it's also strictly less than everything over here. Cool. So that works for our scenario. We have let's check the other else condition, which is when there is nothing to traverse on the right side. So I'm going to remove everything here. This would be our situation, and this is it's a very simple situation, because in this case, if we found the node and the parent, cool, and this is a simple scenario because we can basically look at the parent and check if the node is to the right or the left from the parent. In this case, the node is to the right of the parent. Cool. And we will assign parent right to node left. So we're basically moving the left subtree upwards, and we're kind of forgetting about 13. And that's how you remove the node with just one subtree. 5 is less than 10, less than 9, less than 10, less than 10.25. It's greater than 3 and 3. So this is a simple scenario. There are also other edge cases. I'll leave it to you to find out how they work. But this is the algorithm, and as you can see, it's quite efficient because you're just replacing a few values. Okay, that's the end of this video, and if you're really serious about preparation for your next job interview as a software engineer and you want to step up your data structure and algorithm questions knowledge, then like and subscribe, and I'll be uploading more videos like this.